Hello and thank you. This is the final project for algorithms, CS5800, with Katie Davenport, myself, William Joseph Ridolfo, Rachel Schnakenberg, and Sean Yu. We are applying algorithms to a natural disaster zone to determine the most efficient and effective way of distributing aid in that area and getting aid to key cities. Next slide, please. So the first step involved actually getting the real world data and transforming that into a network. For my teammates, I'm going to be discussing that. Katie is going to be up next, talking about shortest paths and maximum flow. There will be a discussion on the genetic algorithm by Rachel, and then Sean is going to close up discussing branch and bound to solve the traveling salesperson problem as applied to this problem. Now, I'm going to be skipping some of these slides just in the interest of time. So the goal for me was to generate a network of nodes and edges taken from real-world sources in order to facilitate application of a network algorithm. So what I needed to do was first get the actual data regarding buildings destroyed in the earthquake zone. Also get the number of the total, all of the buildings in Turkey and the populated areas in Turkey, to generate a series of nodes, a group of nodes, and then use Google Maps to figure out the distances between those nodes. So the data that I was able to receive was polygons. I had to transform these polygons into points, and then I had to use the points to determine the extent of the disaster zone. Next slide, please. Next slide, please. So the polygons that we got, next slide, please, were very short and small. I had to transform these into points using a slide that was prior. And then I needed to determine the extent of the disaster zones. So there were two approaches that needed to be done here. First was determine the maximum among the minimum distances, i.e. the largest value for all of the nearest neighbors. And there are two ways of doing this. First is brute force, which is an O(n) squared time, or using dynamic programming, which basically cuts the brute force algorithm in half. You can see in the nested for loop here, the for j in range is the only difference between these two, but it is a very effective way of reducing and streamlining time. Next slides, please. So this is the disaster zone before. All of the black dots that you see are buildings in Turkey. This is the disaster zone after applying the nearest neighbor algorithm, the maximum of nearest neighbors algorithm, to all of the buildings in the area after we had clustered them. Next couple of slides, please. In the interest of time, I'm skipping a lot of this. It's all going to be in the report. So what we needed to do then was apply what's called the raycasting algorithm to exclude any building that was not in the disaster zone to facilitate further calculations. What I then needed to do was group these confirmed destroyed buildings into clusters and associate those clusters with known cities in Turkey. I used the dbScan algorithm, which in the worst case, in a very dense area, every point is considered a core point. Best case is O(n) log n. This was approximating O(n) log n for us because the data was pretty sparse. Next slide, please. So eventually what we did is we generated this network here. The nodes were generated from the clustering algorithms associating the cities with each cluster, following the roads, and then using Google Maps to determine the edge weights of each of these. There were some weaknesses and limitations with this. First, there's insufficient data. Second, dbScan is only going to work in areas that are not very, that don't have dense clusters. So if you're dealing with a mega city like Tokyo or an area that has a lot of densely populated things, then this is not the right algorithm to do. The second issue was the nearest neighbors maximized algorithm. Is there a way to even streamline that further? And Katie.
Okay, great, thank you. So for this project, I focused on two algorithms that we covered in our course material. With Dijkstra's shortest path algorithm, I tried to address how we should design a flow network to distribute aid. And I looked at two different scenarios. One source reaching all demand locations, and then sort of two smaller logistic hub sources with the demand locations split between them. With the Edmonds-Karp maximum flow algorithm, I calculated how much heavy equipment can be delivered on these networks per day. So this map represents the input graph for Dijkstra's algorithm. The start node was Seihan, which is a natural entry point into the disaster zone, assuming supplies are coming from larger cities in the north along the main highway network. And then I broke the nodes into two groups. Destination nodes were those with the greatest number of destroyed buildings, 50 or greater, and the transit nodes had less than 50 buildings destroyed. So I added some code to Dijkstra's algorithm that allowed me to gather different data points that I needed to design the networks. Relevant code is highlighted in the slides in red boxes. First, I needed the actual path on the shortest path to each of the destination nodes. One observation was that all paths from the start node go directly to Osmany. So I made the decision to transfer the start node to Osmany and place one of the two transportation hubs at Osmany. I then wanted to understand what the best location would be for a second hub location. And I identified that location by calculating which of the transit nodes had the shortest path distance to reach all of the destination nodes. Gaziantep had the shortest distance, so I selected that as the second transit hub. I then assigned destination nodes to each of the two smaller networks based on which was closer. The results are shown. Gaziantep had 3 destination locations assigned to it in green, and Osmany had 5 assigned in, those are in yellow. The final piece of information I needed was the path from Gaziantep to its designated destination locations, and that is shown below. This slide shows the network representing the single source flow network from Osmany to all destination locations. So the red nodes are those destination locations, the green is the start node, and the gray nodes are transit nodes. Edge capacities, I arbitrarily assigned capacities based on distance and whether the road was a highway, primary road, or secondary road. So I assumed 1 unit per kilometer for highway, 0.5 units for primary roads, and 0.25 units for secondary roads. There were multiple destination nodes that are also sinks. So to deal with this, we create a super sink node with incoming edge capacity set to infinity. This slide shows the 2 smaller network flows for the 2 logistic hubs. So once we had these, we were able to implement the Edmonds-Karp algorithm to calculate the max flow. The larger single network had a max flow of 77 units per day. The 2 smaller logistic hub locations had 70 plus 49 for a total of 119 units per day, representing a 55% increase over the single network. So finally, limitations and weaknesses of this analysis is that demand for heavy equipment is oversimplified and does not accurately measure total or relative need. The networks are designed based on shortest paths rather than where resources are most needed. So future study, how can we design a network that would direct flow in proportion to demand and distance, potentially through linear programming or the genetic algorithm that Rachel will now cover. Rachel?
In my section, I will be speaking about an approach to solving our problem using a genetic algorithm. To restate the problem in my view is, how do we plan a path for convoys delivering earth-moving equipment to cities in need based on both minimizing the overall travel and on the amount of need that each city has based on building damage? I approached this with the view of optimizing a multi-objective problem, and to do this I used a genetic algorithm. Genetic algorithms are stochastic heuristic algorithms based on the biological process of evolution. This flowchart shows the steps of a genetic algorithm. First, an initial generation of solutions is generated either randomly or formulaically, and that's called population initialization. Those solutions are then evaluated by the fitness function, which is a function used to score the solutions based on how well they meet the problem objectives. Next, if termination criteria is met, then the algorithm will output the best solution and stop. If the criteria is not met, then the current generation of solutions will undergo selection, crossover, and mutation functions to create the next generation. This new generation of solutions is evaluated for fitness, and the cycle will continue until the termination criteria is met. The chromosomal representation of our problem solution is a single chromosome where each gene in the chromosome is a city, and the sequence of genes represents the path taken to visit those cities and deliver aid. With this, you could solve the problem using only one convoy to visit cities, but I made the assumption that there would be multiple convoys of vehicles and equipment able to go on different paths to deliver aids to cities. So for the application to our case study, I decided that there would be 3 convoys. In our chromosomal representation, the path of each convoy is in a sequence of the length n/3, where n is the full length of the chromosome, aka the number of cities that need to be visited. A constraint is that each convoy needs to start at one of the designated starting nodes, which were 5 cities on the outer edge of our graph, and that no node is visited twice. Additionally, nodes are able to be used as intermediate nodes in the path. Our problem has 2 primary objectives. One is to minimize the total transportation cost, and 2 is to maximize the priority cost, which is based on damage to the cities. So the fitness function I used was based on those 2 objectives, where overall, we are trying to maximize the fitness function by maximizing the sum of the reciprocal of the shortest distance between 2 consecutive genes in the chromosome, found by Dijkstra's algorithm, and the sum of the weighted priority based on the number of buildings damaged. And that was linearly weighed by the order that they appeared in the chromosome. The output path for the 3 convoys from the genetic solution is shown on the table on the right. Using our implementation, we were able to find a solution tailored to both of those objectives that I spoke about in the past slide. The algorithm found the best solution after 99 generations, as you can see from the plot below, and the total travel distance was 1,822 kilometers. This travel distance may be higher than other approaches, but that's because we're balancing prioritization with minimizing travel distance. Next slide. Overall, I'm satisfied that we found a solution that balances those objective functions. You can see the paths on the map on the right. For future work, I would like to refine our fitness function to better balance the 2 objectives, to explore more advanced techniques in crossover and mutation steps of the functions, and to balance the workload between convoys. And now I'm going to pass it off to Sean.
Right, so I'll be looking at using the branch and bound algorithm to solve the traveling salesperson problem. Next slide. Right, I guess so. Actually, in our class, we already talked a little bit about traveling salesperson, but just to summarize, the problem is to start from a node and then find the shortest path that visits every other node in the graph, and then end at the start node. I think it's applicable to disaster relief, because oftentimes, or you may need to visit different cities and then return to a starting city to get more resources. And as we saw in the course, the traveling salesperson problem is NP hard, or it's reducible from the Hamiltonian cycle problem, and so that's why it is so it's NP hard. And then if you consider a brute force algorithm, it will have a factorial complexity, and it's pretty simple to see, because if you think about it, for a given n number of cities, if you start from one city and then you'll have n-1 combinations, but then if you realize that actually the reverse tour is the same, so that's why it's just n-1 factorial divided by 2. Next slide, please. So the branch and bound algorithm is a combinatorial optimization algorithm, and it's used in linear programming. But when you apply it to the TSP, or traveling salesperson problem, there's 2 ways you can do it. The one way is by considering every single edge. And another way is to, instead of using like a list of edges, use a reduced adjacency matrix. But for the interest of time, I won't go into much detail on how this is calculated. Just know that it's some sort of intermediate matrix that represents the cost of traveling to using the smallest edges. Next slide, please. So over here, I just have the pseudocode for the branch and bound algorithm. But in the interest of time, I'm just going to kind of explain it using the example that of our case study. But first, you start with a node that you choose, and then you consider all of the edges. So like in this case, in this example, the node would be Adiaman, and then the children nodes are the nodes that are Adiaman is connected to. And so for each of them, you would calculate the reduced matrix, and then you would sequentially just keep on traveling through to the using the minimum cost as calculated from the reduced matrix and from its children. So this algorithm is similar to the greedy algorithm, and it also uses a priority queue, which is something that we talked about in the course to store the nodes. And eventually, if the priority queue is not empty, or sorry, if the priority queue becomes empty and the solution is not found, then there's no proper solution. But during the loop, there will be should be an optimal solution. So next slide, please. And yeah, from the results, because we had 5 starting cities that we could choose from, to connect to every single city, the optimal city would be starting from Afton, and the total length would be 1,148 kilometers. And that concludes our presentation. Thank you.